Welcome, welcome, welcome to Miss Lisa's Math and Science. This class is physical science. It's designed primarily for homeschoolers who are taking this for a high school science credit. We're using this book. It is Glencoe Science, Physical Science, and we're also using this book for our lab book, Addison Wesley Science, because, it takes two. Actually, the Addison Wesley has better labs for homeschoolers with everyday stuff. So that's why we're using it too. But anyway, if you like the way I explain things, then you are more than welcome to be here. So welcome, welcome. And we're going to be talking about Chapter 3, which is forces. So in the description will be your homework. So be sure to read that and do it. And watch the videos all the way through. I can see y'all don't know this. As a YouTuber, I can see how long you watch the videos, and people will watch them a little bit and then they don't watch them all the way through. And you need to watch them all the way through so that you understand the whole thing and get it explained to you. So, you can read the book and a lot of it will probably make sense without me, but here's the explanation too, and hopefully you'll like it. All right, so what we're talking about is forces. And remember from last week, the force is a push or a pull. And we started talking about Newton. He figured out these laws, a lot of stuff. He figured out calculus, and he figured out his 3 laws of motion, and he figured out gravity, like all during a plague. And we're in the middle of COVID here, COVID-19. And I haven't figured out anything. So I'm not brilliant like Sir Isaac Newton. So we talked last time about the first law, his first law, and it is an object of motion tends to stay in motion, and an object of rest tends to stay at rest unless acted upon by an outside force. So, and so there's always a force. If something stops, then it's because of some outside force. So now we're going to pick up. It's probably not a surprise that we're going to talk about his second and third laws and also some more things about forces. So what we're learning is physics. So the way physical science works is you spend half of your time on physics and half on chemistry. And I've done it both ways. I've taught the physics first. I've taught the chemistry first. I love teaching chemistry. It's like my very first thing. I was a chemistry major toward the very end where I switched to be more of a biochem major. And I love chemistry. I love teaching chemistry. But I really enjoyed the physics part of physical science. So I like it that we're doing physics first. And so for the first half of the class, we'll talk about physics, and the second half will be chemistry. So you get to do both. And studies have shown that people who take physical science do better later in physics and chemistry. So it's a good introduction. And some people don't go on to take them both. Some people will take like biology, physical science, and then take zoology or forensics or anatomy. You don't have to have to go on and take chemistry and physics. Now, in Georgia, if you're going to college, you need to take chemistry, but you don't have to have physics. You can have physical science instead. But wherever your state is, it'll probably have different rules, and private and public have different rules too. All right, so let's talk about Chapter 3, and we're going to talk about force, mass, and acceleration and the relationship between them. So Newton's first law is really easy to remember, kind of a catchy statement. And his third law is sort of a catchy statement too, but this second one is really a math formula, and it's that force equals mass times acceleration. And so it's the famous formula, F equals ma. And I even heard about a physics club. It was the physics majors at a university, and they needed a shirt for their club, and they just had on it put F equals ma. They're like, that's enough. That shows that we're physics. So it's really an important formula in physics, and it's just to get to the force, you have to do its mass times its acceleration. Of course, the mass has to do with the force. A more massive thing has a greater force when it hits you, right? Absolutely. All right, so you'll do some problems with that. You just substitute in what they give you, and then you solve for the one you don't have. So look at those example problems in your book. Remember, you're going to be using your calculator on these. Make sure that you practice them and that you can get the answers, that you understand their math problems there. So one force that is out there, what causes things to eventually slow down and stop, is friction. And I always do this so you know what friction is. Friction is the force that makes a ball stop. When it's rolling, it'll eventually stop. It's what makes it hard to slide a refrigerator across the floor. It's caused because surfaces are not completely flat. If you can see it microscopically, there's hills and valleys. I always say it's like your fingers, and the hills settle into the valleys, and it causes it to stick. But then, so it's all settled in and stuck, and then you push to overcome the friction, and it starts sliding. When it's still, it's called the force of static friction, and that's greater than sliding friction. Once it starts sliding, the hills and valleys don't have time to go in all the way, and it's more like just the tops of the mountains are going across each other. So it's easier to keep pushing a sofa across your living room than it is to start it going. So sliding friction is less than static friction. Static means still. There's another one, rolling friction. And if you take your two things and you roll them, you can see it has way less friction, as the hills and valleys do fit together, but then they come out. And that's why the easiest way to move something is to put it on wheels and roll it, and it will have less friction. So that's all pretty common sense, isn't it? Another kind of friction you really don't think about is air resistance. You jump out of an airplane, you've gone skydiving, and you're going, but why don't you just, why do you get to a certain speed and then you just stay that speed? You don't keep speeding up. And it's because air has molecules that are resisting you, just like the molecules in the floor that are resisting each other with friction. The air itself will start resisting you. And so things that fall get faster and faster and faster until they reach what is called terminal velocity, which means that they can't speed up anymore because the air resistance is slowing them down to a point where they don't speed anymore. So a lot of times you hear that if you threw a penny off of the Empire State Building, that it would get so fast it'd be like a bullet, and it would shoot somebody in the head and kill them. Turns out that's not true. Pennies are very light, and so they very quickly reach terminal velocity. This terminal, they just aren't going to accelerate anymore, and they don't get faster and faster. They just get a certain speed, and that's what it is, because the air is not going to let them go any faster from air resistance. And so if you did throw a penny off the Empire State Building, it would not be good, because it would hit somebody and it would hurt them, and it would even cut their skin on their head, but it would not puncture the bone and kill them. So now you know that it's going to get to the point where it's not getting faster and faster. And that's why it talks about terminal velocity on page 74. Now, what is causing that penny to fall is gravity. What is gravity? Another thing Newton thought of. And what it is that, and we don't understand everything about it. We just know that every object that has mass has a pull on other objects that have mass. So right now, there is gravity between me and my book that is sitting in my lap. There's gravity between me and the phone sitting right over there, because both of us have mass. The earth is pulling on me because it has a lot of mass, but I'm pulling on the earth too. It's just I'm so tiny and the earth is so big. So we don't really see the effects of gravity until you get to really big things like planets. I have to have some water, sorry. And then the effect of gravity can be felt. The bigger the object, the greater the pull. So the Earth has more gravity than the moon, which is much smaller. If you could just take the moon and set it on the Earth, it would about a bit, I can say this, it would be about as big as the United States. It'd be a circle, with the diameter about the size of the United States. So the moon, we think of it as real big up there, the Earth, up there in space, but it's not. I mean, it is big. It's, it's very big for a moon in ratio to Earth. They say that, like I've read before, that the Earth and Moon can almost be thought of as a double planet because the Moon is so big compared to the Earth. But it's still a whole lot smaller than the Earth. It's not close to the same size. And so there's less gravity on the moon. And that's why, when they did the spacewalks and stuff, they can jump and they can hit a golf ball really, really far because the gravity is only about 1/6 the gravity is here. So I'm sure it was very fun for the astronauts to be able to jump around. So you can read about gravity in your book and you can see the formula. Remember that I told you that the difference between theories and laws in science is laws are so true they're math. So it's the law of gravity, and here's our formula on page 76. It's the force of gravity equals G, which is a constant, a gravitational constant, which was another thing I told you. That these laws are so true that they're math. They usually have a constant with them. It's a number that you multiply like pi. It's a number that's always the same, and you multiply it in the formula. And then you multiply the two masses that have the force of gravity between them, and then you divide it by the distance between them squared. So that means that as things get further apart, the gravity's not so strong anymore. The closer they are, the stronger the pull, and the bigger the object, the stronger the pull. And I always think about, if you haven't seen it, the Schoolhouse Rock on gravity, and it's probably on YouTube somewhere. They're owned by Disney now, though, so I don't know. Disney might have gotten them off YouTube, but it's the song that goes down, 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 gravity, and it's like the 50s, and it's a boy singing, Mary Jean, there's gravity between us, kind of thing. It's the pull of gravity. And then Mary Jean walks away, because the further the distance, the less the pull, because she gets mad at him. All right, so now, as you fall, you accelerate because of gravity. You get falling faster and faster and faster until air resistance makes you have terminal velocity. The pull of gravity on you, the acceleration due to the pull of gravity on you, is 9.8 meters per second squared. A lot of books will round that off to 10. I don't like that. I want it to be 9.8. But that is the acceleration due to gravity. And you use it in a lot of physics formulas. You have to include gravity in it. Okay? Now, what's the difference of weight and mass? Weight is the pull of gravity on you. Mass is the amount of matter that makes you up. So if you took me and threw me into outer space with a spacesuit, because I don't want to die, all the fat, all the bones, all the muscles that make me up would still be there. But I would be weightless because gravity wouldn't be pulling on me anymore. Now on Earth, weight and mass are kind of interchangeable. They have different units, but they're pretty interchangeable, because a lot of times, even when we say we're finding the mass, like the kilograms or the grams or the newtons, it is actually the pull of that it would be the pull of gravity on it. Like we will set it on a thing to weigh it, and how it works is by gravity. So I'll tell the answer in grams or kilograms, but this thing that we're using, this balance, would not work in outer space. In outer space, the kilogram thing whatever you're weighing would just float away. So we're using the properties of weight to find mass, because gravity is always pulling on us on Earth, so we can use that to find out the kilograms or the grams. So you can feel weightless and free fall, and they do this to train the astronauts. They'll take a plane up, and then they just let it fall, and then they float around in the plane. It feels like free fall, and it gives them that feeling before they get out to the space station or to space, wherever they're going. And you can feel that sometimes in amusement park rides, like if you go to the Tower of Terror, or Six Flags over Georgia used to have one called Free Fall, and it was take this little elevator up, and then it would drop you like that, and it would actually accelerate you, so you were going faster than free fall. And I think the Tower of Terror does too. But so there are things that just let you fall. Six Flags used to have one called the Gasp, and it would take you up, and it had a parachute on it. It was so fun. They got rid of the Gasp to bring you Goliath, which I love Goliath, But I want both. I want the gasp and glass. Okay, the next thing is horizontal and vertical motion. So, here I have this little thing. Here you're throwing a dog. Oh, you're throwing a dog. No, you're not. You're throwing a ball for your dog, and the dog's running along here, and you can see the ball going up. Okay? Whenever you have something thrown like this, it has two dimensions to what's going on. It's got the vertical dimensions, the y force, and it's got the horizontal dimension, the x force. So if you take physics, you would spend a lot of time breaking motion into its vertical and horizontal forces, and we use trig. We use the sine, cosine, and tangent with the angle to be able to find out what the horizontal and the vertical component of the forces are. So your book kind of introduces that idea to you, but it does not make you do trig, so don't worry, no trig yet. And that's why for physics you need to be enrolled in Algebra 2 or have had Algebra 2, because you need to understand the trig that you need to do the physics. But what I'm saying is there's just math that you can take these forces, that you can take this projectile motion, you can break it into vertical and horizontal, and then there's math called trig, which are some special buttons on your calculator where you can figure out how much of the force is vertical and how much is horizontal. And it's good. Those are good, fun problems. Okay, there's another idea called centripetal force. It is in your book on page 81, and it's centripetal acceleration. So remember, acceleration is speeding up, slowing down, or changing directions. So when you're going in a circle, you have centripetal acceleration. Centripetal force can be thought of a little bit like this. Is if I had a yo-yo on the end of a string, a yo-yo string, and I'm going around my head, woo, 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 woo. It's more fun with sound effects. What is keeping my yo-yo from flying off in space is that this force going toward the center of the circle on the string, and that is holding it in. So there's a picture in your book of people riding swings. It's sort of like Gotham City crime wave at Six Flags. I love Six Flags. I relate everything to that. We had a Seasons Pass this year, and then COVID hit. And so it's been closed, and finally they opened, and we went, and you have to wear a mask, and it was awful. It was hot. Georgia is hot and humid, and Six Flags is the hottest place in Georgia, and wearing that mask, I thought I was going to suffocate, but I did it because I love Six Flags. But I'm looking forward to them in the fall. I think I can handle my mask a whole lot better than I did in July, so we'll see. Anyway. So there are many amusement park rides based on these ideas. And in fact, Six Flags over Georgia has Physics Day in the spring for physical science and physics students to come and do field trips, and they get to do the amusement park rides and learn about all the forces. And you should do that. You should find out, get your mom to find out about those and see if you can go to the Physics Days at Six Flags. When I taught public school, we would take the classes to Six Flags. And then in our homeschool, too, they allow homeschoolers, too, to participate in the Physics Days. It's not cheaper or anything, but it's just kind of cool because it makes you realize that there's physics behind amusement park rides. So gravity, the book talks about, can be a centripetal force because it is what's going back, holding the planets as they go around the sun, or the moon as it's going around the earth. And there's more about that too that we might talk about later, but certainly in physics. All right, so Newton's first law is an object in motion tends to stay in motion, an object at rest tends to stay at rest unless acted upon by an outside force. Newton's second law is force equals mass times acceleration. And Newton's third law is for every action, there's an equal and opposite reaction. The forces come in pairs, and there is action-reaction forces. Now, that probably sounds confusing, but look, I have a picture for it. All right, so here you have your feet. To move forward, your feet push backwards. So the action is you push back. The reaction is you go forward. You really can see this like if you've ever been on a raft and went to jump off. What happens to the raft? It flies out from under your feet in the opposite direction, right? And instead you just go splash and do a belly flop a lot of times. There's also this kind of, I don't know if you've ever seen this kind of lawn sprinkler. It goes so you have to have the sound effect. As the water's going one way out of it, it makes the sprinkler turn the other way, action, reaction, and it moves. So your book makes the point that why do things move if these forces are equal and opposite? Why do things move? Because doesn't balance forces mean that it has no motion? The key to all of this is action reaction forces are not acting on the same object. If they were and they were balanced and they were equal and opposite, there would be no motion. But they're moving on different things. And I always think of, there's a physics professor I really like. And is that one of the nerdiest things I've ever said? Yes. He's my favorite physics textbook author, right up there with the nerdiness. His name is Dr. Paul Hewitt. And he always says that if you punch a wall, then the wall punches you back. And that's why your fist hurts. And so like if you have a piece of tissue paper, you try to punch it, then you can't really punch it because the tissue paper is too weak to punch you back. So you can't really get a good punch. Now the wall, you can break your hand on. It's because the wall punches you. You punch the wall, but the wall punches you back. They're not acting on the same thing. And then he makes it sweet and says, so you can't touch the world without the world touching you back. So everything is action reaction forces, and you can read about that with the figure skater. We see it. One application of this is rocket. So a rocket burns fuel that expands, and it causes expansion of this gas underneath it, and then the reaction force is the rocket goes off. So you can watch a rocket launching. There's a picture of one in your book. And it's still action-reaction forces. The next idea is momentum. And I mentioned it briefly last time. It talks about in your book on page 86. Momentum, and you know what momentum is. You've heard this before. But momentum comes from mass times acceleration. So which has more momentum? A freight train or a Volkswagen Beetle? The freight train, because it has more mass. Which has more momentum? A paper clip that I throw at you or a bullet that I shoot? The bullet, because it's going so fast, because momentum comes from both mass and acceleration and the velocity and speed. So the faster it's going, the more. It doesn't have to be big. If it's going fast enough, it still has a lot of momentum. But if it's big, even if it's going slow, it's got a lot of momentum. So momentum comes from those two things, the mass and the speed or velocity. So that kind of makes sense because we know we don't want to get hit by a train. One time we lived in Douglasville, and it was right when Pokemon cards were really big. And there was a kid who was looking at his Pokemon cards and wasn't paying attention, and he got hit by the train. So always pay attention to what's going on. Don't mess around with trains. Don't try to go faster than they are and beat them when you're driving. Obey that thing when it comes down, when the arm comes down, the lights turn red. Don't go. You're just not going to win with the train. Trains have too much momentum. They have physics on their side. So always be aware of your surroundings and don't mess with trains. Unless you're like riding them and enjoying them, but don't think you're going to win in a collision with the train. Too much momentum. Now, if you look on your book on page 87, momentum is conserved, which means it's not created or destroyed. It's just changed from one form to another. You've seen this, what it means of momentum being conserved. Okay, so have you ever been sat on a chair and you got it spinning? and you stick your legs out and you go slow. But then you pull your legs in and you go fast. You see with ice skaters, they'll be ice skating and they'll stick their leg out and then they pull their leg in and they do all their arms up. They go, woo, and they get faster. So this is because momentum is conserved, that it tries to maintain. So if the mass is, instead of being spread out, if it's pulled in, then it wants to conserve that momentum so the speed will increase. So read about that in your book, but I think you kind of, if you've ever sat in a chair and spun around and pulled your legs in and out, you know a little bit about that. You've already done an experiment and didn't even realize what you were doing. All right, so that's chapter 3. Come back next week and we'll talk about energy, which is another Schoolhouse Rock, and I want to sing you the song. In the comments, I'll give you some homework to do, and I will also give you some labs to do out of the other book. And the other book has good labs with stuff that's just around your house. So your labs will come out of the Addison Wesley, your reading and your questions are going to come out of Glencoe. All right? So science is great. Come back next time.